Hello and welcome to a new lecture on version control systems and Git. Version control systems are tools used to track changes to source code or other collections of files and folders. As the name implies, these tools help maintain a history of changes. Furthermore, they facilitate collaboration. Version control systems track changes to a folder and its contents in a series of snapshots, where each snapshot encapsulates the entire state of files within a top-level directory. Version control systems also maintain metadata like who created each snapshot, messages associated with each snapshot, and so on. Why is version control useful? Even when you're working by yourself, it can let you look at old snapshots of a project, keep a log of why certain changes were made, work on parallel branches of development, and much more. When working with others, it's an invaluable tool for seeing what other people have changed, as well as resolving conflicts in concurrent development. Modern version control also let you easily answer questions like who wrote this module, when was this particular line of this particular file edited, by whom, why was it edited, and question like when or why did a particular unit test stop working over the last 1,000 revisions. While other systems exist, Git is de facto standard for version control. The comic on the slide captures Git's reputation. Because Git's interface is a leaky abstraction, learning Git top-down, that means starting with its interface, can lead to a lot of confusion. It's possible to memorize a handful of commands and think of them as magic incantations, and follow the approach in the comic on the slide whenever anything goes wrong. But it is possible to understand beautiful design of Git. With that knowledge, it is way easier to use Git as command line tool. Once the data model is understood, the commands can be better understood in terms of how they manipulate the underlying data model. For this reason, we give a bottom-up explanation of Git, starting with its data model and later covering the command line interface. So let's go forward and talk about Git data model. Git models the history of a collection of files and folders within some top-level directory as a series of snapshots. In Git terminology, a file is called a blob, and it's just a bunch of bytes. A directory is called a tree, and it maps names to blobs or trees. So directories can contain other directories. A snapshot is the top-level tree that is being tracked. For example, we might have a tree as follows. The top-level tree contains two elements, tree foo and blob buzz. Tree foo contains other blob, and buzz is a file with contents Git is wonderful, just a single line. Also, we can visualize a tree in such way. How should a version control system relate snapshots? One simple model would be to have a linear history. A history would be a list of snapshots in time order. For many reasons, Git doesn't use a simple model like this. In Git, a history is a directed acyclic graph of snapshots. This means that each snapshot in Git refers to a set of parents, the snapshots that preceded it. It has a set of parents rather than a single parent, because a snapshot might descend from multiple parents. For example, due to combining two parallel branches of development. In Git, combining of two branches, named merging. Git calls these snapshots commits. Visualizing a commit history might look something like this on the slide. In the art on the slide, the blocks with sys correspond to individual commits, snapshots. The arrows point to the parent of each commit. After the third commit, C2, the history branches in two separate branches. This might correspond to, for example, two separate features being developed in parallel, independently from each other. In the future, these branches will be merged to create a new snapshot that incorporates both of the features, with the newly created merge commit shown here as C6. It is needed to know commits in Git are immutable. This doesn't mean that mistakes can't be corrected. However, it's just that edits to the commit history are actually creating entirely new commits and references, which we will discuss later in this lecture. These references are updated to point to the new ones. We know that Git data model contains of three main data types. Let's write them down in pseudocode. Here on the slide you can see. First, type blob. It's just an array of bytes and it corresponds to a file. The second type is tree. This is a mapping from string to tree or blob, and it corresponds to a directory. Commit is the third type. It can be described as structure with set of parents, string corresponding to author's name, string corresponding to message which comes with this commit, introducing changes what was done in this commit, and snapshot, which contains a tree structure, a current tree structure of directory. It is a clean and simple model of history. As we mentioned, an object could be a blob, a tree, or a commit. In Git data store, all objects are content addressed by their SHA-1 hash. We can define methods on how to save and load them from storage. Imagine that storage is called objects. Objects is a mapping from string, hash, to object, blob or tree or commit. We can define a function to store the object in a storage objects. We pass an object to this function and it creates new ID for this object based on its hash. Then we can load the object from the storage using its hash or ID. Blobs, trees, and commits are unified in this way. they are all objects. When they reference other objects, they don't actually contain them in their on-disk representation, but have a reference to them by their hash. For the example directory structure here can be visualized with git lstree head. The tree itself contains pointers to its contents, bus.txt, a blob, and foo, a tree. If we look at the contents addressed by the hash corresponding to bus.txt with git catfile -p and corresponding hash, we get the following. Git is wonderful, which is just the contents of bus.txt file. Let's talk about references. Now all snapshots can be identified by their hash. That's inconvenient because humans aren't good at remembering strings of 40 hexadecimal characters. Git's solution to this problem is human-readable names for hashes, called references. References are pointers to commits. Unlike objects, which are immutable, references are mutable. That means can be updated to point to a new commit. For example, the master reference usually points to the latest commit in the main branch of development. Here we can see pseudocode on how to work with references. References is the storage that maps a string human-readable name to a hash, 40 hexadecimal characters. We can define a function update reference, which takes a human-readable name and hash and store it in the reference. We can define a function read reference, which returns a hash ID for a given name from the storage. We can define a load reference function that accepts either name or ID and return an object from the storage of objects. With this, Git can use human-readable names like master to refer to a particular snapshot in the history, instead of a long hexadecimal string. One detail is that we often want a notion of where we currently are in the history, so that when we take a new snapshot, we know what it is relative to. In Git, that where we currently are is a special reference called head. Here on the right side of the slide, we can see some example of Git history. We have several commits. One reference named master points to commit number 4, and we can see that head reference has changed from pointing to commit number 2 to pointing to commit number 5. Again, head and master is just human-readable references to a hexadecimal hashes. Finally, we can define what is a Git repository. It is the data, objects, and references. On disk, Git stores objects and references. That's all there is to Git's data model. All Git commands map to some manipulation of the commit graph by adding objects and adding or updating references. Whenever you are typing in any command, think about what manipulation the command is making to the underlying graph data structure. Conversely, if you are trying to make a particular kind of change to the commit graph, for example, discard uncommitted changes and make the master ref point to a commit with this hash, there's probably a command to do it. For example, in this case, git checkout master and then git reset --hard to this hash. There is another concept that's orthogonal to the data model, but it's a part of the interface to create commits. One way you might imagine implementing snapshotting, as described earlier, is to have a create snapshot command that creates a new snapshot based on the current state of the working directory. Git doesn't work that way. We want clean snapshots, and it might not always be ideal to make a snapshot from the current state. For example, imagine a scenario where you have implemented two separate features and you want to create two separate commits, where the first introduces the first feature and the second introduces the second feature. Or imagine a scenario where you have debugging print statements added all over your code, along with a bug fix. You want to commit only the bug fix while discarding all the print statements. Git accommodates such scenarios by allowing you to specify which modifications should be included in the next snapshot through a mechanism called the staging area. So here on the slide you can see you did some changes in working directory and you can add them to the staging area using git add command. After that, you commit your changes from staging area to repository with git commit command. After that, you can do everything again to create a new commit from changes you have already done. Let's move on and talk briefly about git command line commands. The basics. First of all, use git help to understand what command does. Use git init to create a new git repository with data stored in the .git directory. Git status. This command tells you what's going on with your current state. Git add adds files to staging area. Git commit creates a new commit. It is crucial to write good commit messages. So I encourage you to visit this link and see how it works and see how to write good commit messages. Git log shows a flattened log history. Git log with these flags can print a graph of your history. Git diff with file name show changes you made relative to the staging area. Git diff with some revision and file name show difference in a file between snapshots. Git checkout revision updates your head and current branch. Git checkout revision switch your current branch. Here I provide you a link to online book that named Git Pro. There you can find any git command with description. I encourage you to walk through it and you will learn a lot from it. Let's talk about commands which you will utilize to work with remotes. Git is a tool to share your work with others. And to share your work with others, it is needed to push your changes and your code to some server. That's called remote. You can use git remote command to list all remotes available to your current repository. You can use git remote add to add a new remote to your local repository. Git push to send all your commits to the remote. Git branch to set up correspondence between local and remote branch. Git fetch to retrieve objects but not merge. And git pull to fetch, that means retrieve objects from remote and merge it with your local. Also, there is git clone command that allow you to download repository from remote and set up a local version of it. Here again the link to the Git Pro book. In my opinion, it is preferable to start using Git with graphical user interface tools such as SmartGit or GitKraken or GitHub Desktop. These tools are great to start using version control, minimizing effort to memorize all commands and their combinations. But with concepts that have been provided earlier in this lecture, you are able to work with any of given options. That means with command line and with GUI apps. So let's talk a little bit of these apps. GitKraken provides simple user interface with project, graph, and interactive merging tool. You can navigate through commit history and do rebasing with drag and drop of your mouse. But it doesn't work well out of the box with large repositories with thousands of branches, like SmartGit does. SmartGit interface is more complex and harder to cope with. But if you are already proficient in other GUI, it will be not so hard. GitHub Desktop provides very similar to SmartGit functionality, but it is not available on Linux systems. Choose what you prefer most, to use graphical UI or command line, and start controlling versions of your code. So that's it for today. Thank you.